So today's paper we are going to look at is the good counterfactuals and where to find them. A case-based technique for generating counterfactuals for explainable AI. So this was a paper that was recently submitted at the ICCBR 2020 conference by the UCD team, Mark Keane and Barry Smith. It's a very interesting paper because counterfactuals has a strong alignment with the techniques from case-based reasoning. So it makes sense to link this type of explainer with the case-based reasoning research. So looking at the abstract, they argue that counterfactuals, technically, these counterfactual cases can be generated by permuting problem features until a class change is found. Then they say counterfactuals are also psychologically, they are much more causally informative than factual explanations. And they say legally, they are GDPR compliant. So basically what a counterfactual is sort of like a experience or in this case they call it a case. You can think of it as a training case, a training example, and essentially you present something that is similar to the current situation to help the user understand the outcome of the machine learning model. So one thing that is specific about the counterfactual when you look at the literature and explanation is that, as I've written here, typically refers to an attempt to convey the internal state. They don't attempt to try and convey the internal state or logic of an algorithm that leads to a decision, but what they are doing is a counterfactual describes the dependency on the external facts that led to that decision. So this idea is slightly different from other explainers. So for example, if you take a salience map or something, they are trying very hard to explain the weights and how those weights impact the final output. But here with counterfactual, they are interested in the raw input data and how you can use the raw input data to help with the explanation. So that's the interesting difference between counterfactuals and some of these other explainer techniques. Right, so I will just go through some of the key highlights in each section. So what they motivate this by is saying that CBR has always been, or case-based reasoning has always been a central role, played a central role in explanation, as predictions can readily be explained by cases, akin to human reasoning from precedent or examples. So that is analogical reasoning has the advantage that you can, through analogy, explain situations. So they say, indeed, in this Keane and Kenny's paper, which was presented in IJCAI 2019, the twin system approach explicitly maps opaque deep learning systems into CBR systems to find post hoc explanatory cases for their prediction. So what they did there was they had a deep learning architecture which was twinned with a case-based reasoning system. And a lot of that paper focused on how can we make sure that the deep learning model input outputs link up with what the twin system CBR input output is providing. Because if the two systems are doing two different things, then you cannot use the CBR system to explain the deep learner. So they did various metrics to prove that there was a strong alignment between the two. And then on that basis, they used the CBR system to retrieve cases and post hoc after the decision was made to explain that decision on the basis of the twin system. So what they're saying is for this paper, where they are using counterfactual cases, they are expecting there to be an architecture similar to that, which is have a deep learning algorithm twinned with a CBR-like system. So underpinning these counterfactual cases is this thing called nearest unlike neighbor, or you can call it none or NUN. So basically, what is the nearest unlike neighbor? It is something which is your nearest neighbor, but has a decision or a class different from the decision that was just predicted by the model that you're using to give you the decision. So then they indicate why such counterfactual explanations are useful. They provide these two analogies, two types of explanations to explain why a counterfactual explanation is good. So imagine you have a loan system that indicates to a customer whether or not the customer can get the loan. So one way of giving an explanation could be this first sentence: you were refused because a previous customer had the same salary as you and they were refused a loan for this amount, right? But what they argue is in counterfactual research is, rather than just saying the obvious there, it is far more beneficial if we can say something like this: if you asked for a slightly lower amount, you would have been granted the loan. So this, they say, explain that this is actionable knowledge, something that the user can do to change their situation. And that is far more useful than just saying you were refused because this particular reason. So then, I wonder how to close this thing. Oh, sorry, just that. Is there a way to close this thing? Oh, right. Okay, so where are we now? Right. So now what they want to do is, if they were motivated that counterfactuals are a good way to do explanations, now they want to talk about, how do we measure the potential of counterfactual explanatory coverage in a given case-based system. So by case-based, you can think of it even as a training set, right? So in previous work, they did a lot of work on this concept of predictive coverage. This word here, predictive coverage. And in this paper, they are going to look at how can we characterize or quantify this idea of a explanatory coverage. Given a data set, given a case base, how can we say the potential or the explanatory potential or the explanatory coverage this particular case base might have? So that's what they're trying to come up with here. One other point worth mentioning about actionable information. I think actionable information is what counterfactuals provide, and there are three things that make them useful. One, it will inform and help the user to understand why a particular decision was reached. Two, it will provide grounds to contest adverse decisions. And three, it will help to understand what could be changed to receive a desired result in the future based on the current decision-making model. So I think I found this idea of why counterfactuals are a good way to explain is because they have actionable knowledge, a very interesting concept, because a lot of the explanation research is focusing on, oh, let's go into the black box and try and explain the logic behind the workings. But that is not very useful in some cases for end users, because the end users want actionable knowledge. So I felt that was a very interesting point to extract. So, and when we talk about counterfactual explanations, they give an idea for the type of template this explanation might look like. So they might say your prediction Y, they say score Y, but this is nothing but the prediction. Y was returned because variables V had these particular values. If your variables V had these other V prime 1, V2 prime values, and everything else remained constant, then your prediction would have returned Y prime rather than prediction Y. So that is like a natural language type of template that we could use to explain to let's say present the explanation from a counterfactual. Okay. Um, so then they go on to show this example of what is a good counterfactual and a bad counterfactual using this blood alcohol content case base, right? And here they have a test case, 80 kilograms, duration, I suppose the person was drinking 1 hour before, or gender male, whether they had a meal, so they haven't, number of units of alcohol, and this is whether their blood alcohol content is over a particular threshold or whatever, right? So what they want to know is which of these is a good counterfactual. So they obviously identify the first one as a good counterfactual because if you look at most of the uh, attribute values, they are quite similar. So you can see the weight is similar, gender, meal, units, all similar. The only difference is this 1.5 hours. Whilst in this one, you can see this is not a very good counterfactual because this is possibly not the nearest unlike neighbor because there are several attribute values that are different from the original test case. So essentially what they're demonstrating here is what they mean by a nearest unlike neighbor, where although the classes have changed, the attribute values are very similar. And so what we are looking at are cases that are in the boundary area because that's where you're likely to find the nearest unlike neighbors. So they move on to then talk about the counterfactual promise. Yeah, so what they're saying is counterfactual also encourage to have the human in the loop in the decision making because obviously if you are providing actionable knowledge, then it allows some interaction with the user to try and understand what they can do differently to change the current prediction. And in the beginning of the paper, they say one of the advantages of the counterfactuals is that it is very close to this GDPR compliant issue. And although in the paper they don't explain clearly what they mean by this, there's another paper written by researchers from Harvard Law School, and they provided some interesting points, which I thought I should highlight here. So, counterfactuals, their usage would help to resolve two primary objectives to a legally binding right to explanation. So, the first point for this is that explaining the internal logic of automated systems to experts and non-experts alike is a highly difficult and perhaps intractable challenge. And second, that an excessive disclosure of information about the internal logic of a system could infringe on the rights of others, either by revealing protected trade secrets or by violating the privacy of individuals whose data is contained in the training dataset. In contrast, counterfactuals allow an individual to receive explanations without conveying the internal logic of the algorithm or black box beyond the limited set of dependencies and are less likely to infringe the rights or freedoms of others than full disclosure. Assuming reasonable limitations are set on the number of counterfactuals that must be provided, counterfactuals are also less likely to provide information that reveals trade secrets or allowing gaming of decision-making systems. So essentially, this is again highlighting the issue that unlike other explainers, it is also closer to the GDPR compliance because it provides actionable knowledge that is useful rather than just talking about what is going on inside the black box, which in this case can also reveal some trade secret which you don't want. Now they say, okay, if counterfactuals are so good, what are the issues in finding this counterfactual? So they come up with three things: prolixity, sparsity, and plausibility. So prolixity. Currently, most size systems generate counterfactuals using random perturbations and search, making them very prolix. So there's a lot of them generated, but not necessarily good ones. So what they say is, what we want to do is address this issue by looking at this type of loss function here. So what is this loss function? So they have D is the distance between a particular instance and its counterfactual X prime. And there is also this lambda and a function. This function is nothing but the prediction for the counterfactual X prime minus the, I suspect this is the actual prediction, which is also Y prime. So you want to make sure that they have a different class, and also you want to look at the nearest neighbor aspect of the counterfactual and the case. And what they're saying is they want to maximize lambda and presumably minimize the distance between the case and its counterfactual. And for the distance, they basically use a standard Manhattan distance, and they suggest normalizing it using the median value here, and then they explain why these things are suitable. Then what is the point here? So yes, the use of median absolute difference rather than the more usual standard deviation also makes this metric more robust to outliers. So that is what they argue here. Then looking at sparsity, these methods also prefer to solve the sparsity problem. All commentators argue that good explanatory counterfactuals need to be sparse. That is, they need to modify the fewest features in the selected counterfactual. So that is that idea that they need to have a different class, but the features should be minimally different feature values. That's the property of the sparsity. And then they say, looking at the cognitive burden on humans, they are suggesting that there's a preference that the changes are a single feature between the two items, or in their threshold, they say, based on this evidence, although there's a bit of a jump here from what is in the literature in this paper 49, where they say a single feature change is good, they make a small jump to say, based on this evidence, we operationalize the sparsity of good counterfactuals as items with one or two feature differences versus bad counterfactuals, those with greater than two feature changes. So one might say, okay, this is a little bit arbitrary that they have come up with two features, but I guess what they're trying to get at is what is the minimal number of features that need to be different between the two cases before one can be the counterfactual of the other. And I think this plausibility concept is the most important one, because in standard perturbation, when you perturb and create some cases, you might generate some cases that are not nonsense. They are nonsensical, or probably they are not plausible. So what they are saying is the final problem is that of plausibility. That is, the counterfactuals generated may not be valid data points in the domain, or they may suggest feature changes that are difficult or impossible. And then they go on to give some examples where things like you cannot change gender, or you cannot ask someone to earn a huge number of huge salary difference, because that is not practical, and so on. And so they use these three concepts to motivate that actually, rather than perturbing and trying to generate counterfactuals, why don't we look inside the case base to derive counterfactuals from existing cases in the case base? So I think that is the key concept that this paper is trying to push forward. So here we propose that rather than generating counterfactuals by blind random perturbation, a SI system should use the training data or case base to find suitable counterfactuals, right? And then now, at this point, they come up with a research question, which I feel they should have maybe stated right at the front. How many good counterfactuals are naturally available in a case base, or more simply put, what is their counterfactual potential? And what they're going to do is come up with some um, quantifying equations to try and establish this potential. Right.
Normal.
So let's say, so the important thing is this idea of how do we compute explanatory coverage in a case base. So they do some interesting work here. First, they've taken a whole collection, 20 UCI data sets, and then they've characterized features in the each data set, number of classes, number of pairs, although I'm not sure how they came up with this value, because when I calculated some, they don't make sense to me. We can discuss that later. And then what they do is for a selected case, they pair it with another case if there is a difference of one feature, difference of two feature, three feature, four feature, and greater than five features. And then they see how many such counterfactuals are existing in this case base. And what they find here is there aren't a lot, right? So if you look at two differences, they found that in one difference is none of them. Two difference, they had the back data set, iris data, votes. Those are the only three. And then the others, you have to change a few more features before you can actually find the counterfactuals. So another way of thinking about this is that data sets where you would get this type of nearest unlike neighbors must be data sets that are difficult, because they have to have cases that are in the boundary. So to me, this in a way suggests that the iris and the votes are probably slightly harder data sets than the other data sets, because that's why they have some cases in the boundaries while the others don't. So it'll be interesting to know how a model learned on these data sets, what sort of accuracy they achieved based on the percentage of counterfactuals that exist in the database.
Is it not one of the ways I read into it normally is counterfactuals are basically a method for you to determine specifically what your decision boundaries are. And the way I was reading into it was actually a little bit different, because the my understand from what it looked like was that these were slightly unrealistic in that they anticipated that the decision boundary was elucidated by just one or two features, which is unlikely to replicate reality. And so the iris dataset, I think, is an outlier because it only has four features anyway. So you know that it all decision boundaries must be elucidated by at maximum four features, and that's why you probably start to see them at two feature changes and three feature changes and so on. Back in votes, it may well be that it's just the decision boundaries are easier to identify um, because of the small numbers of features and stuff. I think it reveals two big problems about the counterfactual approach they recommend, which is that you anticipate that users understand the features of your data set, and that you anticipate there are no feature dependencies within your data set. Because if there were feature dependencies, it's very, very unlikely that there will be one or two features that cause the difference at a decision boundary. And so I found that, I don't know, I found what that means is the one or two, for me, what it means is the one or two feature thing is probably less important than this idea of trying to identify the decision boundary based on the minimum number of features that is relevant to your data set or situation, I guess.
So I think, Kyle, you made a good point about the redundancy of features. I think that's an issue they have not addressed. I think that's quite important because if there are features that are redundant, then it becomes harder to achieve this hard constraint of two difference. So yeah, that's a very useful point. But they move on to then say if you don't focus on feature differences, you could have a similarity threshold and use that as a way to identify counterfactuals. And in fact, in their later experiments, that's what they do. I just want to touch upon this point about the boundaries. So the idea is that if you can find nearest unlike neighbors with as fewer feature differences, or in other words, you can find nearest unlike neighbors with a greater similarity, those are data sets where there is confusion in the boundary, right? So that is for sure, because those are the cases that are on the boundary, otherwise you will not find them. So the fact that these there are three, only three of them have two difference, to me suggests that um, even though iris has only four classes, three classes and only four features, that is probably one of the reasons that it is harder, because there's probably not enough features to easily make it a separable data set. And perhaps that's why we see it having a column two differences having iris 0.3%, while the others haven't. So I would say that in a way, this also highlights some of the mixture that you see in the boundary. And obviously, when there is mixture, there's high entropy, and when there's high entropy, it becomes harder to differentiate the class boundaries.
Yeah, I can see that argument, and I suppose the way I'm coming at it from is it it's more about the data set coverage. I think we can't anticipate it means that the decision boundaries are any less or more complex. It's just if this is a real data set, then it means that it's more likely for for actual cases to appear on that decision boundary. Does that make sense? Because a lot of these others have 10,000 cases or so, and um, back has 10,000 cases, so it's quite a bit larger than some of these other data sets. It may well be that abalone, if we collected a further 5,000 or so, some of them would have cases that appeared on the decision boundary. Now, it might not be the case, it might not. It's
Yes,
more just a
yes,
situation where it's more likely
yes.
for things to appear at these decision boundaries, I
Of
guess.
course, yes, absolutely. It very much depends on the data set that we currently have, clearly. And based on the data set that we have here, we can say that the ones which are having nearest unlike neighbors that are closer to boundaries are obviously the ones which are harder to differentiate in terms of the decision boundary. And absolutely, if you add more data, these boundaries will have a good chance of changing. Yeah, that's for sure. Okay, so the case-based technique. So let's go to how they generate counterfactuals. Let's look at some of the equations here. So I think the most important equation is equation 2, but let's look at the equation 1. So given a case-based C, they try to establish the explanation coverage set for that entire case base. So here what they say, C can be represented by a coverage set equation 1, and degree of explanatory competence can be estimated as the size of the coverage set as a fraction of the case base, which is equation 2. So here, given some counterfactual C prime, which is an element of the case base C, there exists a particular case C, which is an element of the case base different with the counterfactual not in the case base, such that um, that particular case C is explained by the counterfactual C prime. Okay, so essentially this XP coverage set T consists of all the cases that can be explained using counterfactuals, right? Then we go to what is the XP coverage of the case base. So basically that is the set of cases that can be explained divided by the size of the case base. So this gives you the explanatory capability or the competence of the case base. So that equation 2 is probably the most important one here. Now they come up with this other research question. Can pairs of cases and their corresponding good counterfactuals guide the search for novel good counterfactuals for new target problems that are otherwise without a good counterfactual? So, okay, so from here KP coverage set C found counterfactuals for some cases, right? What they're saying in this research question is for those cases that don't have counterfactuals, can we come up with a technique to generate them? And this is where the novelty of this paper really exists. So let's see how they use Casebases to do the generation of counterfactuals. Right, so what is equation 3? So for any given case base, we can generate a corresponding case base of these explanation cases for use during counterfactual generation. See equations 3 and 4. So this is this idea that when we pick up a case and it's counterfactual, we want to make sure that the difference of features is less than or equal to 2 and that their class prediction actual classes are also different. Then we say that XC is a explanation case for a case C and its counterfactual C prime. I think at some point they changed the C prime and C incorrectly. I can't remember where. Now in equation 4, what they are saying here is that they have, okay, so now that we have a pair of a case explanation experience consists of a case and its counterfactual. So that is C comma C prime. That itself is a case, and those pairs together form a case inside the explanation case base. So this explanation case base consists of pairs of cases where a particular pair is a query or the case and its explanation counterfactual case. That's what they're saying here. So I guess essentially what we basically have here is we can think of like a adaptation case base where a single case consists of two parts. Like this, it has a query and it has its counterfactual, and together they form a single explanation case which is put into this explanation case base. So this idea is very similar to what we used to say about adaptation case bases for people who may have worked in that area. Right. So now here what they do is we see in this gray area the different pairs that we can have in a explanation case base. So explanation case here X and X prime, it's the case and it's counterfactual, and they are on either side of the boundaries because they have different predictions, right? So for example, if you take this one here, this is one case and the counterfactual is here and they're on either side of the boundary. Similarly, they have a second case, explanation case X and X prime here, and another one explanation case Y and Y prime here. So what they are saying is, if you want to find a generator explanation for a case that doesn't have a counterfactual, let's take a particular case. Let's say, for example, this P here, this one. Let's find it's a similar case in the explanation case base. And because this gray one here has its counterfactual, let's use that counterfactual to somehow generate a new counterfactual for P, because P doesn't have a counterfactual. How do we do that? We keep some features fixed and those feature values are transferred here. And the parts which are unfixed, the areas which are the two features which are different, we move those values into this particular P here. So thereby we have generated a new P prime. So now this case P has a counterfactual P prime, which it didn't have before. So that is the idea that they are suggesting. So in order for us to do this, it was very important that we had an explanation case base with these pairs of explanation cases. These are the gray cases. And in this side, they show in a picture how they copy and paste from the query case and from the counterfactual case. So that's quite interesting because it makes you also wonder if you had a explanation case base of these pairs, can you use a deep learner to learn how to generate these counterfactual explanation cases as well? Because this is sort of done heuristically, but perhaps this idea might also be translated into a generative model in a deep learning type of idea. So I'll move to some of the explanations because these are the steps that discuss how the case is generated. I mean, they also talk about a scenario. For example, what happens if we generate a particular case? Let's say we generate this case here, right? But it turns out that when you check the model prediction for this Q prime, it is still on the wrong side of the boundary because it needs to be a nearest unlike. So what they say is, okay, if we want to move it toward the other side of the boundary, what can we do? So what they suggest is we take this query case here and find the nearest neighbors and try. So if you find a nearest neighbor here, try and use the feature values from that nearest neighbor to do an adaptation step. So basically this part here, sorry, what happened there? Yeah, so this from moving from here to here is retrieval, then moving from here to this part is called adaptation. So they have two different steps with which they can evaluate the goodness of their method, and that we see in their evaluation results here. Also, I just want to highlight this point, which I thought was a very strong assumption they made. They say another advantage of this approach is that because it reuses actual feature values from real cases, it should, they say here, it should lead to more plausible counterfactuals and better explanations. So this is a strong assumption, and maybe we can discuss whether we believe they managed to prove this in their experiments or not. So here are their experiments. So they run it on 5 data sets, and they look at two things, two metrics, right? The first one is the fraction of target or query cases that can be associated with good counterfactuals, explanatory competence, and B, the distance from the target query to the newly generated good counterfactuals. This is the counterfactual distance. So in the first one, what they are looking at is whether using their approach to generating counterfactuals, are they able to increase the explanatory coverage or explanatory competence of their case base. That is their equation 2 that they're exploring. And then in the second one, they are saying, okay, we can generate counterfactuals, but how close are these counterfactuals to the actual case that we're interested in? So here, this is about similarity. So to a little extent, I feel that this second one is it's a proxy method. Ideally, you want users to tell you whether the counterfactual explanation cases generated were good or bad. But in the absence of users, that's the best they could do. So I suppose they have some very interesting results that in the first case show that the explanatory coverage of their case base is significantly, or not statistically, but in terms of values, quite high, that the increase is very prominent here. Yeah. So the
Yeah,
baseline is, if you just don't use retrieval, don't use adaptation, just use the existing counterfactuals. This is the green line, and then if you just do retrieval, you get to blue, and then if you do adaptation, you get to red. So huge differences. So what they are showing here is that their approach can generate uh, quite a huge number of counterfactuals into their case base, which they didn't have before, right? Then I guess this one is basically trying to prove that, okay, by introducing these new counterfactuals, how close are the counterfactuals to their own queries? And what they show here is they do retrieval or reuse, adaptation, or out of these two, they pick the closest one. So what they're saying is, even if you generate even if you generate a counterfactual just by retrieving, it is always better to try and adapt it as well, because the adapted counterfactuals tend to be closer to the query phase. So I think that is what this is trying to show in that picture there. Um, so I will just go to the conclusion so we have some time to discuss. So I think one of the key issues was we need a way to generate counterfactuals. Current methods have the problems of sparsity and plausibility. Therefore, we will look at a case-based approach. And I must say, I really liked the idea of how they do retrieve, reuse, and adaptation to create these counterfactuals. And they say they have clarified the definition of good counterfactuals. They have proposed new idea for explanation competence, and they reported significant new evidence for the utility of this novel technique. And I think that third one is a bit strong, because the word significant and the fact that no users were involved makes it a little bit questionable. But nevertheless, I thought the method was extremely good. Um, for us, for the discussion, I suppose there are some interesting disadvantages. So for um, counterfactuals as a minimal form of explanation, counterfactuals are not appropriate for all possible scenarios. So there are some scenarios this is good for. Counterfactuals don't provide statistics, so therefore it is difficult to do any analysis on fairness or bias. Counterfactuals might not be suitable if we are working with images for image recognition. I'm not sure how you would, could you just show, say, I'm not sure how that works. But in many of the other uh, situations where actionable knowledge is important, I think counterfactuals are very useful. For me, I'll be interested to know ideas on this generative approach, and how, after generating these case pairs, whether we can use some kind of a sequence to sequence generative model to generate counterfactuals based on a explanation paired case base. So I will stop there and ask people to give me some suggestions, and